So what we're going to do today is I'm going to give a little bit of a presentation to give some insights into a topic that I find very exciting, and I hope you will too. And then Allie from Fortune is going to come up, and we're going to have a discussion, engaging you in the audience. But before I get started, let me ask a question, show of hands. Who here is in the audience because quantum was in the title of the session?
Oh,
Who
wow.
here is in the audience because AI was in the title? It's super interesting. It's roughly 50-50. Now let me ask another question. Who among you would call yourself an expert in quantum? You're a practitioner, you work in the field, you're a researcher. Who's maybe heard about it, you've read something in the news, you've been excited by some press announcements, and who here has no idea what the fuck it's about but really wants to figure it out? All right, well, there's a few of you. So what I want to do today is share with you some insights into the convergence of two technologies. Now, I know, because I looked at the rundown of sessions, that there are not only a lot of quantum sessions, there are a metric F-ton of AI sessions. But this one is going to be a little different. This is going to be about how AI is driving new science in the way that we as humans can control nature. I'm going to tell you about how we're building intelligent machines that allow us to access nature on the most fundamental levels. So you come away with hopefully a deeper appreciation of how exciting this convergence is. And at the end of the talk, I'm going to give you just one more thing that will hopefully be exciting to some of you. Now, what we're really interested in is the development of a new kind of technology that uses quantum physics, in particular for computing. Many of you will have heard of the field of quantum computing, whereby we leverage the rules of nature on tiny size scales, called quantum physics, in order to encode and process information to solve problems that are otherwise pretty hard for regular computers. Now, this is a field that's gotten a lot of attention because a few years ago, the Boston Consulting Group wrote a piece that said this is an $850 billion market opportunity. Now, not to be outdone, their rival McKinsey came out and said, no, wait, this is a $2 trillion opportunity. It's since escalated from there. But the reason that it's mooted as such a huge, high-impact opportunity is because quantum goes into so many places. It has the opportunity to change the way we do, frankly, rather mundane things, like building schedules for transit networks, but also much more exotic things, like the way we do pharmaceutical drug discovery or exotic financial modeling, or, aligned with what many of you may be expecting, new forms of artificial intelligence powered by quantum algorithms. This is the way that the problem, the intersection of these two fields, is almost always posed. It's posed that a new form of computational engine, a new kind of computer, a quantum computer, can power next-generation AI agents. Maybe it will bring about AGI. But I'm going to invert that for this talk. I'm going to share with you insights into how AI is allowing us to access nature in order to make quantum computers a reality, to achieve the holy grail in our field called quantum advantage, when the quantum computer actually beats anything else. I want to emphasize to you, these things are real. After my talk, you can log in to a machine from IBM or from our new partners at IonQ and AWS, from an announcement earlier today, and you can go, and using our software, you can run algorithms, run programs on real quantum computers. And I want to emphasize, not pretend quantum computers that are simulated in another computer, real quantum things. They really exist. But in order to understand how these things that do exist can get us to some profound new applications, we need to take a step back and ask where we are today. Many of you will be familiar with a photograph like this. These are microprocessors. These are the devices that power the modern information age. These devices work because of a kind of material called a semiconductor, most famous of which is silicon. Semiconductors are materials that either behave like electrical conductors, allowing electricity to flow, or like electrical insulators, blocking the flow of electricity, and can change between those two states depending on the application of another electrical signal. Controlling the flow of electricity with electricity is, believe it or not, a phenomenon that comes to us from quantum physics. It is the quantum physics that describes how many, many electrons, the charge carriers in a solid material, behave to give rise to this behavior. And we can do absolutely magnificent things with this technology. It powers the information age, but you can literally put 1 billion of the special switching elements called transistors in an area the size of your fingernail. You can do amazing things with this technology. And you know it's transformed all our lives. But despite that, the way we build technology, the most advanced technology we broadly have in the consumer market, is quite crude. It's a little bit like this. We start with a giant pile of stuff. If we learn the right rules, we can shape the stuff into the forms we care about. Here, a giant pile of sand shaped into a sand sculpture. You can make really magnificent things, just like you can put 1 billion transistors in an area the size of your thumbnail. But it shouldn't escape our understanding that if instead of starting from the giant pile of stuff, if instead we look more closely, we see that there is new complexity that emerges. Instead of just a homogeneous pile of tan, now we see that some grains of sand are seashell and some are stone. Some are transparent, some opaque. Some are rough, some are smooth. This complexity is completely absent when we only look at the giant pile of stuff. It is incumbent upon us to look more closely to see this complexity. And so the same is true in the way we build technology, because we now have the opportunity to start thinking about building from the most fundamental particles of light and matter. Thinking about individual atoms, shown here as the canonical cartoon representation, as our grains of sand, as our building blocks for technology. Now, before anybody objects and says, what a ridiculous idea of building things out of individual atoms, that's a photograph from my academic lab at the University of Sydney of one atom. It's a real picture. It's taken with a camera that's almost the same as the one in your mobile phone. That one atom is trapped in a special electromagnetic bottle called an ion trap. And with this atom, we can access the rules of nature on these tiny size scales, the rules of quantum physics. Now, what's interesting is at these scales, nature is quite different than what we typically experience. Instead of thinking about atoms like little billiard balls that bounce off one another, we have to think about them more like waves. Waves that spread out in space. Waves that interfere with each other or even with themselves. And it's this wave-like nature of matter that we want to exploit in building this new technology. When we think about encoding information, of processing information in a quantum computer, that wave-like nature gives us some really different characteristics. Here, in a picture of 300 atoms or thereabouts, we can encode the quantum version of a bit, a qubit, like the 1 or a 0. And with 300, there are 2 to the 300 possibilities of all the 1s and 0s. And in our simple English language description, which is not accurate, but it's close enough, we can represent all 2 to the 300 possibilities at the same time in air quotes. Remember, that's not exactly accurate. That's how English approximates math. 2 to the 300 is a pretty big number. 2 to the 300 is about 10 to the 100, a Google. A number so big that if you tried to write out all the different combinations of zeros and ones, you would run out of matter in the universe before you could do it. And yet, you can encode that information in just 300 atoms if you know the right rules, the rules of quantum physics. Now, for the, I think, few experts in the room, the trick is, how do you take that capacity and turn it into something useful? Because by itself, it is not useful. We have to figure out how to process information, not just think about this really immense storage. But if we can do it, we can, again, in air quotes, compute the uncomputable, problems that are practically impossible, the problems that I told you about in pharmaceutical drug discovery, in finance, and of course, in new forms of AI, new forms of machine learning. So if we think about going back to this as our individual grain of sand, the technology that we want to start building from, our task is to figure out how to do something useful with it. Now, the unfortunate reality is, as soon as we reach in and try to control nature on these tiny size scales, everything goes in the toilet. We break it. Our grubby hands destroy all this complexity we're looking to exploit. It's a little bit like trying to reach into a meadow to pick a delicate flower. But because our disgusting, huge, clumsy, classical hands reach in, we shatter and destroy the flower as we try to pick it. But we're not trying to build a quantum computer from one atom. We're trying to build a quantum computer from thousands or hundreds of thousands or millions or more. And so when we reach in from our world down to the quantum domain, what is left behind is a massacre. We destroy everything we touch. This is the problem. This is why there are so many announcements in the media these days, because everybody is thinking about how do we overcome this challenge. What we discovered in my academic work, in my role as a founder at Q-CTRL, is that machines can have more delicate hands than humans. Machines can be better at manipulating things in the quantum domain than we can. Now, at Q-CTRL, we build AI-powered infrastructure software that solves this problem, the fact that when we typically reach in, we just destroy, we massacre all the quantumness that we want to exploit. And what I want to do is show you just one example of how we do that. Many of you will be familiar with the idea that we program computers with languages at different levels. We program in graphical user interfaces, we program in things like C or JavaScript or whatever, and we programmed all the way down to assembly and ultimately machine language. Now, almost none of us ever touch machine language, but it's familiar at least that we program machines, classical machines, with ones and zeros, because we can use those ones and zeros to determine whether the transistor, the switch, is on or off, whether electricity is flowing or not flowing. That's the machine language that we typically use in a computer. Quantum computers also have a machine language. But the machine language is now the structure of little blips of laser light or of microwaves. The same kinds of signals that we use in modern telecommunication, but now used to manipulate matter at the quantum level. It is the shape of those pulses, those little blips, that determines the machine language, and also that determines whether or not it's effective. Now, humans have rules that we use to figure out how to shape those pulses, but we're really bad at it. We know the course rules, but the results are only okay. What we did a few years ago and published in the academic literature was an experiment where we connected an AI agent directly to a quantum computer. And we asked the agent to design a new machine language. For any of the AI pros in the room, this is based on something called deep reinforcement learning. But in this case, all that happened is the agent would test the machine. The machine would send back an answer. What is the output of that experiment? The agent would learn from those experiments and decide what to do next. And it would do this iteratively. Now, the agents we build are very special. They're designed to account for the fact that measurements in quantum computers are very costly. But this is the simple idea. You let the machine, the intelligent machine, figure out what to do. And it did it. It came up with something that looks kind of similar to what we humans design by coming up with the right rules. But the shape of the pulses, of the microwaves, is just a little bit different. Now, you may say, well, okay, it only made a coarse approximation of what you already came up with as a human. But what we found is that what the machine built was way better. It was more than 2 times more precise. That is, how accurate is the operation that it implemented. But more importantly was the second metric. Quantum computers change a lot. They drift over time. You tweak up the knobs with your human hands, you walk away to get a coffee, you come back, and everything is different. This is why we have so many PhD students. But this really is a big challenge. You tune it up, it goes out of spec. Most of the commercial machines, every 6 hours, have to be taken offline to be recalibrated. Now, the agent was learning how to craft a machine language while this was happening, while the machine was changing. And what it figured out was a new solution that didn't need to be calibrated not over minutes or hours, but over months. We came back and tested this machine language more than a month later, 49 days later, and it was that day better than the best human-designed solution. Our agent actually learned something called robust control without us ever asking it to. The machines figured out the right way to manipulate nature. And so if you look at the way we build our software products, which have a whole range of techniques that we put together to reduce errors in quantum computers so you as a user can get better results, more or less in every step, the purple boxes are what we do, we've now incorporated AI agents to replace the grubby human hands. The AI agents are just better at most of these tasks, whether it's machine language or a whole range of other tasks. For the few experts in the room, things like compilation and measurement error readout mitigation. AI agents are doing better, enabling us to get better results and to abstract away the hardware. And the performance that we get is really quite incredible. With the AI agents solving all these problems for us, the likelihood that the machine gives you the right answer goes up by like 1,000 times. Orders of magnitude improvement. Now, fundamentally, the way it's working is it's a little bit like the AI agents build noise-canceling headphones around the quantum logic elements, the qubits in the processor, that allow us to get these incredible outcomes where the hardware is resilient against all the stuff that conspires to break it. So you see that AI agents are already driving major progress in the development of quantum computers. But I wanted to share with you just one more thing on a slightly different topic. We've talked a little bit about one application of quantum technology called quantum computing, where everybody is yearning to achieve quantum advantage, where the quantum computer is better than the alternatives. And I showed you how we're using AI agents to help get us there. But there's another vertical called quantum sensing. Quantum sensing, instead of using the quantum things to process information, use quantum things in order to sense the environment around us. And one particular application that we've been focused on is how we can use quantum sensors to navigate when there is no GPS. Now, I'm going to guess that almost everybody in the room got here using a location-based service. Uber, Google Maps, Lyft, whatever. GPS absolutely rules our modern lives. But it's very delicate. And because of adversarial action around the world, this is now something that is considered to be at risk. It's known that it would cost about $1 billion per day if there was a short-term GPS outage in the United States. Way more expensive if it's prolonged. But this is not just a matter of economic impact. This is actually being used as a weapon of economic sabotage. Since March of 2024, over 1,000 commercial flights per day have been subject to GPS jamming, where somebody, you can guess, interferes with the GPS signals and drives planes off course. There was actually a crash not long ago over Central Asia related to this. This is a major consideration in flight safety. And so we've been thinking, what can we do with quantum sensing to fix this? And our view is we need to get back to what we used to do. Who here is familiar with the scouting activity of orienteering, right? You're given a map, you're dumped in the woods, and you have to use your eyes to figure out where you are on the map. You say, oh, there's a river, there's a tree, there's a hill. This is where I am. Use your eyes, you compare against the map, and you position yourself, and then you navigate. Okay, that's great if you are dumped in the woods, but what if it's really dark? What if it's over water? What if it's cloudy? What if you just can't see? Well, Earth has all sorts of other signatures that are not visible to our eyes, but are visible if we have the right kinds of eyes. Even though we think about Earth's gravity as constant, or Earth's magnetic field is pointing north, it has bumps and wiggles that are really unique fingerprints. And if we have the right set of eyes, we can see them. We fortunately have maps of these things because mapping this is how the resources industry discovers oil, natural gas, critical minerals. This has been done for decades. We have maps everywhere. We need the new eyes. So we've been focusing on quantum sensors that allow us to see these variations. And in partnership with Airbus, we recently ran a series of test flights of a new form of quantum-assured navigation system where we focused on asking the question of whether AI-powered quantum sensors could actually help us navigate. And the answer is a rather emphatic yes. Not only were we able to navigate, but we achieved true commercial quantum advantage in quantum navigation. For the first time, a quantum solution outperformed the best classical alternative, head-to-head on the same airplane. It has never been done before in any application. And we didn't beat it by a little bit. Right? In a lot of these fields in AI, like you're so psyched for 1%, 3%. We beat it by 50 times. No satellite, no GPS. GPS is off. In fact, this is so precise, it's like an archer hitting a target bullseye at 1,000 yards, but the great part is it doesn't matter how far away you move from the target. You always hit the bullseye because you're just positioning yourselves on the map. AI is powering quantum technology to make this real. Now, we talked all through this talk about how AI makes quantum real. And you've now seen a real application that we're about to announce. So, we're going to the news in the next few weeks. Stay tuned. But this is only one part of the cycle, because quantum, as we make new kinds of sensors to observe the world and collect information, and we build new processors, brings us back to new forms of AI. AI needs data, AI needs processing. This is a $6 trillion industry and a $2 trillion industry in a virtuous cycle. And so I'll leave you with this question. If we're driving AI agent development now to power new forms of quantum technology, are the machines designing their future selves? So thank you very much. I hope this has been interesting. I'm now going to invite Allie from Fortune to come up, and we're going to have a discussion, and we'll take your questions. Thank you.
Well, to be clear, I'm not taking any questions. Those of you who raised your hands that finds this intriguing, that's me. I'm solidly in your camp. You know, I imagine there are already questions for Mike. I want to ask one of my own, so if you're thinking about your questions, feel free to start lining up shortly. But I want to lob your philosophical question right back at you and see what you think the answer is. Mike, are machines helping build their future selves right now?
I think, you know, I posed it this way because it's obviously intentionally thought-provoking. I think it's useful to talk about this with a real reality-based foundation, right? We have been exploring how quantum computing can impact the next generation or future generations of AI and machine learning. And there are a few hopeful opportunities that we've identified, but we've also crossed off a bunch.
Like what have you crossed off? What's a no-go?
Honestly, this is a little bit beyond me. There are very specific problems in machine learning that have been demonstrated, actually by Scott Aronson at University of Texas here, have been demonstrated cannot deliver a quantum advantage, right? Maybe Andre in the audience can answer the question for me. But so it's important to disambiguate. Just because we have quantum computers doesn't mean we suddenly have all these AI agents that are AGI or whatever, but it is, anytime there's a new computational tool, we'll exploit it, right? And so that plus the fact that there is this opportunity for better what's called representability, that the way we encode information, like in the large language models, can be richer, can take into account different kinds of information. That to us is very exciting, but we have to wait and see. Right? So the reason we have focused on AI driving quantum is that that is real, that is really happening, it is delivering big outcomes, and it's inspirational to ask how that can feed back. We don't know yet.
We don't know yet. We're going to go to some questions over here since there are already questions. If you could say your name and ask your question, please.
Sure. Charles Donnelly. In addition to PN junctions being quantum related for compute, recording heads and disk drives have been doing tunneling now for over 5 years as a Nobel Prize back in 2008. So you have another example of existing quantum being useful in compute. The input signal that you were showing that was AI optimized, was that controlling the trap to keep the qubit entangled, or was that about the EMF for an input signal to process a gate?
Thanks for the question. So first of all, there are many demonstrations of what we call the first generation of quantum technologies. Lasers are an example, coherent states. And so you're absolutely right that PN junctions and other things in semiconductor physics fall into that. The specific example that I showed here is one of many in our pantheon of developments. That particular one is designing the microwave pulse, the shape of the waveform, IQ modulated, if that's familiar to you, that defines the interaction between two qubits in a superconducting device. It's a device from IBM, commercial device, and these devices are fabricated on a chip, and they naturally don't talk to each other. But if you activate them with the right pulse of microwaves, it's actually a couple different pulses, then you can induce an interaction between them. And so this is shaping that waveform in order to generate the interaction.
Very good, thanks. And congratulations on the gravity mapping.
Thank you.
Hi, my name is Adil Khan. I'm here from right here in Austin. My question for you is really for startups that are looking to get into the space, trying to find product market fit and initiate product discovery of how we can find applications. When you're looking at this $2 trillion plus $6 trillion market, do you currently see a lot of that being in this infrastructure layer, loosely termed, helping different people who already have applications and executing those on quantum hardware? Or do you feel like that unforeseen world and sensors that you were talking through, there's a lot of opportunities out there for new startups to come in and say, find brand new start to finish applications. And finally, what is your advice for startups getting into the space to be able to get themselves exposed in this type of thinking where you're exploring the edge, where a lot of undiscoverable, unsensed, and trying to make an impact?
Great, thank you very much for the question. For context, we at Q-CTRL are an infrastructure software company, right? We are the first infrastructure software company. We're the first ISV to ever integrate with a major quantum cloud platform with IBM in 2023. We build the stuff between the applications, the programs that people run, and the hardware. So we think that as a first mover in that there's a huge value capture, right? If you look at the other companies that look like that in classical computing, because this is what every venture capitalist does. They look for a model and they try to match what you're doing to something they know. You look at companies like VMware, right? It's behind the scenes in everything we do. You don't really know about it, but it makes everything work. More recently, OpenAI, it's an infrastructure software company, right? They're making AI infrastructure that others use to build products, right? Of course, they build products also. Brocade, Juniper Networks, Citrix, all these companies are multi-$10 billion companies or more, and they all make stuff work in the background. Now, for personal reasons, I like that. I like being the guy behind the guy. But from a business perspective, we think there's a lot of value. The problem is it's really, really effing hard, right? It is ridiculously hard because you need to be an expert not only in software engineering and the applications and all those things, but you also need to be an expert in the very lowest levels of how you manipulate the hardware, right? And this is actually a really interesting dynamic in our field. A number of companies have risen and fallen. One of them even went SPAC and then went out of business because they tried very early to be applications companies when the hardware was not ready for abstraction and high-level programming, right? You say, oh, I want to run my quantum optimization for pharmaceuticals or whatever, and you run it, and you've made this beautiful pen and paper algorithm that should give you, I don't know, 1, and you measure it, and it's always 0, right? And you don't know why. It's because the hardware suffers from us reaching in with our grubby classical hands. We, as experts in the hardware manipulation, started at the bottom and built upwards. It's really, really hard to do that. And it's impossible, in our view, to start at the top and say, I'm an expert in quantum algorithms, and then figure out what to do at the lowest levels to manipulate the quantum transistors, if you will. So my advice is, I don't like to give advice, but I'll answer your question this way. Pay attention to the timing risk in quantum, right? That if you just come out and say, we're going to build applications for quantum computers, don't fall into the trap that a number of other companies have fallen into where the hardware was not ready for them. Now, we are making the hardware easier to use. We're abstracting it. We're making it more powerful. But it's essential to understand that quantum computing is not as mature as cloud computing. We're working to get it there, but it's got some time. And if you build your business with that understanding, you can do well. Otherwise, just learn. Learn, learn, learn.
Thank you so much.
Thank you.
Hi. Thank you for a great talk. My name is Allie Garfinkle. I was really interested in the last thing you said about quantum sensing and using that as a commercial quantum advantage. I've been curious if, the use in AI in achieving that goal, was it used to do some sort of error mitigation to make your quantum hardware more noise resilient? And then to that, you have all these companies trying to go towards like fault tolerance. And I'm curious what you see as the applications of AI in facilitating maybe either when we have like fault tolerant quantum computers or getting to that stage.
Great, thanks. Did you put up your hand when I asked about experts in the room?
Yeah.
Very good question. So the first thing is that, of course, I just glossed over it for time. In the quantum sensing application, the biggest challenge is that that particular demonstration is a magnetometer. So it's magnetic map matching, it's called. And guess what? Anything that moves that's metal makes a lot of magnetic fields. So all the engine parts, all the electronics, everything on the airplane makes all sorts of magnetic noise. And even though magnetic map matching as a concept has been around for literally decades, it's never really worked. because the process of what's called denoising is so nasty. And we figured out a way that combines human intelligence with physics-constrained AI in order to solve this so-called denoising and map matching problem. And we did it in a very specific way that, maybe to also address the previous questioner, was driven by a product focus. We said it can't just be science, it actually has to work for the customers. And so I'll just give a little bit more on this. What had been around for a long time was old school filtering technique from electrical engineering, where the only way to make it work is when the airplane takes off, it has to, for like half an hour, fly in this cloverleaf pattern to calibrate the algorithm. And like, can you imagine taking off from Austin and then you to fly for 30 minutes in a cloverleaf before you can go to your destination? It's utterly untenable. And that's why there's been no progress for decades. We figured out a way where the algorithm learns on the fly. It figures this out as it goes. It doesn't require any special calibration maneuvers. And that is transformative for both commercial aviation and defense missions. Now, to your other question about fault tolerance is really a shorthand for can you build really, really big quantum computers? We think that there are two parts to this. One is you just have to make the hardware as good as, you can operate it as well as you possibly can. And we think AI is an important tool in that, like all the software we build. The other part is you have to do this thing called error correction, where you find the things that actually do fail and fix them. And there are roles for AI agents in making that process efficient. So we think it's just kind of going to be everywhere. Frankly, it has a new name, AI. We've used these tools for a long time, control theory and machine learning and et cetera. But with all the development in AI, it's giving us new tools and new capabilities. Thanks very much for the question.
Thank you.
Right. And just so you know, guys, whoever's in line, those are the last ones. I want to get to some of my own questions too, but please go
not
ahead.
important.
Thank you so much. Yeah.
No, not compared to the audience, I'm not, but I still
you.
want to get in a few.
Fair enough.
Sure.
Go ahead, please.
So that is example you gave with the satellite, was that completely self-contained, or was there some sort of entanglement on the ground or somewhere else? I've heard of quantum entanglement. Is that involved?
That's a great question. There's no quantum entanglement used in this.
Okay.
We have
What is quantum entanglement?
quantum
by the way?
entanglement. It's another very good question. Quantum entanglement is one of these unusual properties of quantum physics. We sometimes talk about quantum physics as spooky or weird or whatever, because the rules are so different. This is a rule that basically says that quantum systems can be linked together in a way that we can't quite see, and the only way to describe them is they're actually one composite unit. And so if you take two nominally separate things like atoms and you entangle them, they're no longer really two atoms, they're one thing. And so if you separate them by the distance of the known universe, manipulating one instantly affects its partner, right? It's this very unusual phenomenology. And so people think about using that for communications. We're not using that in this case. It's a magnetometer on the airplane with this AI software. It senses, it sees the magnetic fields, and then it figures out where it is on a map.
Go ahead, please.
Thank you. My name's Meredith. I firstly wanted just to say what an effective communicator you are. That was a really excellent presentation. And then I have a couple of questions. So
Very kind of
firstly,
you, thank you.
you're welcome. Firstly, I was wondering about the interaction between advancements in narrow use cases like the one that you've been speaking about and the progression towards more general quantum computers and whether that sort of technological pathway is common or separate. And then my second question is a bit of more of a blue sky one. I wonder if you have any thoughts about any changes that might be needed in the industry to move it on to the next level.
Great, thank you, Meredith, for the questions. On the first one, I think maybe I'll answer it with an analogy or a historical analog. Have you ever heard of the ENIAC? The ENIAC was the world's first digital electronic computer, the first computer that behaved in a way that operationally, mathematically, is very similar to the one in your mobile phone. It was at the University of Pennsylvania. It was commissioned in 1947 or something. That machine, which at the time cost like $5 million, it was a wartime effort, had one application in mind: artillery shell trajectory calculation. It was the only thing that they thought was worth building the machine for. They spent a lot of, $5 million in those days, right?
Back when that really meant something.
Yeah, that was a lot of money. And now think about Fitbit and Facebook and like all these things that emerge from that. So narrow use cases that drive technology forward, if they're sufficiently high value, can motivate much bigger developments that have very broad impact. And we think that a lot of the things that are emerging, and in particular these unsexy problems like logistics optimization. How does FedEx figure out how to route packages? This is a mathematically very hard problem, but it's massively economically relevant. Those problems can drive the technology forward. And then to general things in the sector, I think the biggest thing, frankly, is that the hardware has to get better and more accessible. We're obviously doing our part with our partnerships with IonQ and IBM and Rigetti and Dirac and others to help drive that along. But for the most part, people have been trying to generate applications like the equivalent of writing Facebook with pen and paper. It's exceptionally difficult. And we need the machines in the hands of developers so they can try programming, so they can play. That's what we're all pushing towards, but that's the big change that's happening now. Thank you.
Go ahead, please.
Hi, I think you answered part of my question with that statement. But in a panel earlier this week, and also I'm one of the casual quantum guys that you referenced earlier, I heard that the average person still doesn't understand quantum or how it'll benefit their lives, similar to how the average person didn't really understand blockchain until it was applied to some application. Quantum, based on what you told me, seems to provide value primarily through businesses that pass it down to their customers, like airlines using it for safer navigation. The customer gets safer flights. Are there emerging applications where end users will experience direct benefits from quantum computing, or is that still too early to assess?
It's an excellent question. I think the reality is that right now this is a B2B industry. And when we're talking about use cases for quantum computers or quantum sensors, we're broadly thinking about how large enterprises can adopt this technology. So that's optimization, it's rail scheduling and routing, it's financial modeling and all these things. I am not aware at this time of any real end user focused applications that emerge specifically from the advent of quantum computing. Now, that's not to say it won't happen. Right? You know, we started out calculating artillery shell trajectories, and now you have Fitbit and Facebook. I just think it's a journey to get there as the machines get bigger. Great question. Thank you.
I'll allow you time for many
no, it's
questions
okay,
here,
please.
but I'll try to be short here. I love this idea of convergence of different technologies. Overall, they are the ones that create the future. I was thinking about if we join AIs and quantum computing has an ability to calculate massive amounts of data that we don't even know yet. Would it be fair to say that in the future, I want to jump a little bit in the future in the philosophical side of it, would it be fair to say that we might end in uncertainty, like we might erase uncertainty so that it would be able to calculate and understand so many scenarios and different possibilities that at one point one AI powered by quantum would be able to eliminate uncertainty? And if so, and the second part of the question is that, what happens to society if we don't have uncertainty, since it's something that we always had since forever?
Thanks. Well, I think the last week of stock markets has told us what happens when there's a lot of
I was going to say, you've really left us with something light here.
Yeah, well, I mean, easy question.
Your first question is very profound, and I probably will struggle to give a really significant answer to it. I just don't know. Now, what I can tell you is that quantum computers broadly are not actually good at processing large amounts of data. This is maybe a misconception in the field, so I hope my answer can help you with some insight that perhaps you didn't have before. Quantum computers don't have a concept of memory. They only have input-output. And so even though there are many bottlenecks in data when we talk about AI or whatever, people sometimes say, well, quantum computers will be relevant in processing all the data we're collecting. It's not true. Quantum computers are not good for big data problems. Now, what can happen is that the way we represent data can be richer, can have these quantum effects, the entanglement, right? These correlations between things that are only describable with quantum physics. And it could be that those features in an AI model could give us new capabilities. This is what's exciting, because it's just so different than what we do today. But we just don't know. Ultimately, whenever we measure something, we measure a quantum thing, it becomes classical again. So the uncertainty, all these 2 to the 300 things, when you measure it, it just becomes one number, right? So, you know, the most interesting thing that I've thought about and posed to a big tech CEO not long ago was, imagine you have a future. This is a company that had a particular interest in IoT at the time, Internet of Things. Imagine you have distributed quantum sensors that communicate over a quantum network to quantum computers. So all the data stays quantum the whole time. That is the recipe for something really unusual, really different in terms of building new quantum AI models, because the only quantum AI application where we know the quantum computer is better is if the data comes from a quantum sensor and stays quantum into the quantum computer. It's the only time we know you get a win. You can train models more efficiently. So we're thinking about how you keep things more quantum instead of turning off the quantum and then feeding it to the next device, but it's all for the future.
Thank you so much.
Thank you.
I moderate a lot of panels, and I'm trying to think of a time in recent memory where there have been more questions from an audience. And I guess my question for you then maybe, and this is not where I thought we were going, but it did just occur to me, is I think people imagine a Marvel movie, maybe when they think about quantum. Why do you think it captures people's imaginations?
I actually think it's a disservice that our community has done.
Really? Okay, why?
I think it's.
I feel like that's a hot take.
In a sense, I have a lot of those.
Perfect. Let's hear. We're going to hear all of them.
In a sense, it was like, some of you may know I live in Australia now. It's a little bit like how in the 1980s Australia built its tourism around Crocodile Dundee. Like it was a really aggressive positioning, but maybe it wasn't the smartest thing. You know, quantum physics is not counterintuitive. It's not spooky and it's not weird. It's just different. And instead of telling people, don't anthropomorphize the rules of physics of single atoms and electrons, just accept that it's different, we tried to craft this narrative about spookiness and difference and all these things. I honestly don't know why that happened. I don't know what the driver was. But I think it led people astray. I think it made people think, well, it's so weird, even these scientists can't talk about it, and so this is not for us. One of the questioners earlier was saying, you know, basically this is indiscernible from Web3 or blockchain or crypto or whatever. It's all the same, it's all spooky gobbledygook. I think that was a bit of a cell phone in the scientific community, and I hope with talks like this, we can help to bring it back to reality and show that this is just the way that nature works. It's not spooky, it's not weird. Like maybe some of the math is a little different than what you've seen before, but it is the most accurate theory ever devised to describe nature. Nothing comes close. Builds all of our technology. So let's just accept that's how it is, not try to anthropomorphize atoms, and keep going.
So no anthropomorphizing the atoms. That's
Yep.
rule number one. You've used the word spooky a couple of times. Why the word spooky? What is it about quantum physics that is so different? Like I think it's sort of been implicit, but I think we should make it explicit.
That's right. So this actually goes back to the dawn of the field.
Tell us about the dawn of the field. We're here already.
Sure. Basically, quantum physics is the one instance where Einstein was just wrong. Einstein insisted that this theory that others, Heisenberg and Bohr and so on, came up with was not correct, because it says that everything is probabilistic. Right? Before I was talking about it's all this quantum superposition it's called, and then you measure and it just turns into one classical thing. It's probabilistic in the sense that it's not hidden information behind the scenes. There's just this very different set of rules, and then you observe and the probability collapses. Just like, you know, you're playing blackjack and there's a probability you're going to hit blackjack and a probability you don't, and when the flop comes, well, you know one way or the other. So in this case, Einstein insisted that this probabilistic approach was just not right. And there have been tests. There's one called a Bell test that really asks the question, who's right? Einstein or the others? The others are right. Einstein is
and
wrong.
that feels spooky because people are
And
like, wait,
one
wasn't
of the-
Einstein right about everything?
One of the pejorative descriptions that Einstein used was talking about spooky action at a distance to describe this phenomenon of entanglement. It was a pejorative slam on, like, this is too stupid to be real. So I'm going to call it spooky. And then that stuck because there's all these bits of probability, and you manipulate this one thing over here, and something over here feels that there was a thought experiment called the Einstein-Podolsky-Rosen experiment that posited this and other things. And so spooky entered the vernacular there. And actually, a guy who not long ago worked at the White House, Office of Science and Technology Policy, I'm going to
Are you going to call somebody out right now?
No, well, no. His name is Charlie Tahan. He's a great guy. I hired him into the government when I was working at the DoD like 20 years ago. And he actually wrote an article in 2008 called Spooky Technology, when he was trying to motivate bigger government investment into this field. And while it hasn't, we don't call it that broadly, the terminology is in the vernacular, but also it's widely used in the science community.
So you don't like, for what it's worth, as a horror movie fan, I do like the word spooky, but I see why it hasn't been the best possible PR. While we're here, other big misconceptions about quantum?
That it's hard. It's not. It's no harder than anything else. We've just fallen into this trap of characterizing it in this way that's unintelligible. It's spooky, it's otherworldly, all these things. It's not hard. If you can go and understand how waves in a pond build up and how they cancel each other out sometimes, that is basically all the physics that you need to know. That's how quantum computers work. That's how all of this technology works. It's just waves, ripples in a pond interfering, and we have a set of mathematical rules that describe waves in the quantum domain. The math is a little bit different, but it's exactly the same stuff. Now, you have to learn it, right? But I think
Like anything else.
the way people my age, which is old, learned it was driven by the historical progress of the field. You start with atomic structure, then because like all these people at the turn of the 20th century were trying to figure out why when you would shine light on atoms, some light would get absorbed and some wouldn't. Why when you would heat up an element, sometimes it was orange and some other one was blue. People were trying to figure out these things that they were observing, and quantum theory emerged from that. Now, people like me learned quantum physics in the same order, which is idiotic. Because like one of the first things you learn is this completely wrong model that you know, as a student, you spend all this time learning the so-called Bohr model of the atom, and then the lecturer is like, sorry, it's all bullshit. And then you go on to the next thing.
It sounds like there's improvement to be had
I
here.
think, well, what's happening is actually with quantum computing coming around and being popular, we're developing new ways to teach the material that gets rid of the spookiness, that doesn't start with these, early 20th century observations of light emission from metals and things, and goes right to, we want to process information in a different way. What can we do to understand that? What can we do to make that intuitive? And then we'll fill in the mathematics that supports making that formal. So I think this is happening right now. We actually build an educational technology product, Black Opal, that you can use. There's a free version. Black Opal quantum computing is awesome. We want to make it easier, but I think, again, our sector has done itself no favors in the way we've taught this historically.
Do you think that sort of the public volatilities of certain quantum stocks, for example, has sort of not helped that narrative either?
Oh, I think it's massively helped. People are paying attention.
Oh, so it's good.
So,
That's good.
So when, some of you may know that Jensen Huang at NVIDIA made a comment that quantum computing was some years away. First thing to say is he doesn't know what he's talking about. He's a very, very smart guy. He does very impressive things with GPUs, but he is not an expert in quantum computing, right? And so he made an assertion that was, I would say, mildly informed at best, and it drove the stock market because he runs the most valuable company in the world.
Regardless of whether he knows anything about quantum.
Well, I mean, let's be clear. I'm not saying he's not smart and he doesn't have some basic understanding, but he is not an expert. He's clearly not keeping track of this on a day-to-day basis. But then Microsoft and Google came out with dueling announcement because it was impacting their stocks, and all these other startup stocks that went SPAC instead of IPO a few years ago, they all skyrocketed, and they've all crashed back down. But irrespective of the volatility in the market, people paying attention to this as real and as warranting the attention of Satya Nadella and Sundar Pichai and even Elon Musk, like the fact that these people are speaking about quantum technology openly as something that's coming is better than AI, and completely ignoring it, right? Which is what happened for about 2 years.
Well, I was actually, who here in the last 6 months has seen a headline with the word quantum in it? Raise your hand. Do you think there would have been that many hand raises 10 years ago?
No way.
No, okay. So what's
Not a
changed
chance.
other than Jensen?
I mean, the biggest thing is that there is now an industry. I mean, I've been in this field since, shamefully, 2000. And
I won't tell anyone.
everybody knows. And you know, at the time, this was 100% in academia and a couple of national labs, 100%. And it wasn't until 2013, 2014 that you started to see industry engagement in it in a meaningful way. Investments from Microsoft. You saw Google buy an academic team out of UC Santa Barbara. Things like that happen. And frankly, as you know, American culture, for its good and bad properties, pays a lot of attention to business, to industry, things with financial impact more than perhaps scientific or cultural impact. And as soon as industry began paying real attention to the quantum tech sector, right, there was a 2013 front page article about Microsoft investing in quantum computing, like real basic research. That started to shift the narrative. People started to pay attention. I'll throw it back to you. You know, what made you and your colleagues start paying attention?
Truthfully, probably that. If large companies are talking about it, well, then journalists have to know what it is. Journalists get curious, start covering it, and then I'm sitting here with you, and we're having a conversation about GPS instead of just academic use cases. I think that's probably how it happens. I also think it does capture people's imaginations, and as any reporter who's looking to tell a story, it is compelling. Like there is an idea of a quantum computer. Like I actually asked you, I think the first time we talked, was what does a quantum computer actually look like? Because it's the sort of thing that this is real. And I think that I don't know, I think it makes a difference. Does that make sense?
Yeah. Well, now, I mean, these things are commercial,
Yeah.
right? They don't all look the same. There are a few different versions of them,
Yeah.
but, you know, it's very different than just the lab prototypes.
One of my favorite sort of odd facts about covering AI is that there are a lot of researchers who will look at me sometimes and be like, we don't actually 100% know how LLMs work. There's a little bit of magic. There are little things that we don't fully understand. Is there anything about quantum that we don't fully understand?
There certainly are, but I want to answer your question in a slightly different way.
Sure.
There are other people in the community who have tried we'll treat quantum like LLMs approach and actually have just thrown AI agents blindly at the problem. There's one company that does this quite prominently.
You feel very positively about it, I can tell.
It doesn't work. It doesn't work. So what you need to do is constrain the AI agents using physics intuition, right? You need to give some bounds because the AI agents, there is no way that they're just going to work out of the box because they haven't been training on stuff with, you know, the entire internet worth of data. So blind AI application doesn't work. But the thing that we just don't understand fundamentally about quantum mechanics is why the property of measurement observing is so different than everything else. We just don't know. You do all these things, it stays quantum, you can manipulate, et cetera, and then as soon as you look at it, it's no longer quantum. We don't know why. It just works. It just works. You can make calls on your mobile phone because of this. And I was a really bad scientist because I said, I don't care. I'll let somebody else figure out why it's different. I want to figure out what else we can do with it. But it's a topic in what's called the foundations, or quantum foundations, right? Trying to understand why it's so unusual.
It just works.
It just
You'll
works.
let someone else figure it out. All right, last question. Next time this audience sees a headline with the word quantum in it, what do you want them to remember?
Q-CTRL is making your flight safer. I'm not joking. We take seriously the idea that the technology we're building is supposed to have impacts on your lives, not just be for my own shits and giggles. I'm sorry, I should have prefaced that I have a rather foul mouth. I know we're at South by Southwest, but I apologize to anybody who doesn't like it. You know,
In the last
minute. You know, I feel like servant leadership kind of mentality in the operation of our business, and we really, really want to deliver big impacts that improve people's lives, whether it's in more efficient transit scheduling or it's in flight safety, and we are absolutely committed to making this work. So I hope you'll think about that. The news will be out in a few weeks, and so you'll see it and you'll be like, oh yeah, and hopefully you'll think fondly of this session.
Thank you all so much, and thank you, Mike.